Today we also discuss on important topics. Okay, after inverse function theorem, we also discuss some example of this. Okay, so we start now. We write if r square to r square be a function defined by if xy equal to e to the power x cos y and e to the power x sin y. Okay, for all xy belongs to r, then f1 xy equal to e to the power x cos y and f2 xy equal to e to the power x sin y. Note that f is differentiable on note that f is differentiable on r square with jfxy equal to here e to the power x cos y and here difference e to the power x sin y and here e to the power x sin y and here e to the power x cos y equal to this one. How this one we derive? We know about that del f1 by del x, del f1 by del y, del f2 by del x, del f2 by del y. Okay, then norm of this jf equal to e to the power 2x. Okay, now this one is for xy belongs to r square. Now we're going to further discussion of that. Hence if dash xy is invertible at each point xy belongs to r square. Hence for xy belongs to r square. Okay, hence for xy belongs to r square, there exists an open neighborhood in which f is invertible. Okay, so we also discuss one important theorem. This theorem also inverse function theorem, and next we also discuss one example of this. Okay, now we also going to discussion about some monotonicity of some function. Okay, we erase this example. Now we're going to monotonically increasing or decreasing function. We know about it, but now we discuss also monotone functions. Okay, right here let E be a subset of R. Let E be a subset of R, and let if E to R be a function. If E to R be a function, then f is said to be monotonically increasing. Then f is said to be monotonically increasing. First one, if fx less than equal to fy, for all xy belongs to E with x less than y, and f is strictly increasing, and f is strictly increasing if fx less than fy with x less than y. Suppose that I is an interval. Here some problem again create, why I don't know. Oh, this problem is vanished. Now I am going to forward. Now suppose that I be an interval, on R, and let if I to R be a strictly increasing, if I to R be a strictly increasing function, let xy belongs to I with x less than y, then fx less than fy, and if x greater than y, then fx greater than fy. So x not equal to y, so x not equal to y, this implies fx not equal to fy, then f is 1 1. Hence f is invertible, hence f is invertible and f inverse exists. Okay, so f is strictly increasing, then f is 1 1, so then f is invertible. Okay, we also know about it. Next we erase this portion and going to further discussion of some example of strictly increasing function. Here if 0 closed open infinity to 0 closed open infinity be a function defined by fx equal to x square for all x belongs to closed 0 infinity, and x less than y implies x square less than y square implies fx less than fy. So f is strictly increasing function. Okay, so f is strictly increasing function, then f inverse exists, and f inverse defined on 0 infinity to 0 infinity is given by f inverse y equal to square root of y for all y belongs to 0 infinity. Okay, then we also see here this portion. Okay, f inverse dash a of x0 equal to 1 by f dash x0. Okay, also see this one, but now we are not interested about that, so we erase that portion and going to further discussion of another portion of collection of linear operator from Rn to Rm. We denote let L Rn to Rm, okay, be the collection of linear operator with a collection of linear operators from Rn to Rm. Okay, obviously this Rn to Rm be a vector space. Okay, linear space means vector space. Now we also denote norm of A equal to, okay, if A belongs to this, then this equal to supremum of norm of Ax by norm x, norm x is less than not equal to 0 and x belongs to Rn. Okay, then here A belongs to L of Rn to Rm. Then obviously L Rn Rm, this one norm be a norm space, okay, and obviously this one is complete. We are not discuss now this one, okay, we just discuss this one is a norm space, and obviously we check about it, but now I'm not interested on this, so we erase that portion and going to one lemma. Okay, we erase that portion and going to one lemma. This lemma says that let T belongs to L Rn to Rm. That means some operator from defined from Rn to Rm such that norm of T less than 1. Then I difference T is invertible with I difference T whole inverse equal to summation of n equal to 0 to infinity t to the power n. Okay, we have to prove that. So how we see this? Also write proof here and going to forward. We note that norm of t to the power n equal to less than equal to norm t whole to the power n belongs to n. This implies summation n equal to 0 to infinity t to the power n norm of this less than equal to n equal to 0 to infinity k to the power n, this less than plus infinity. Okay, this implies that n equal to 0 to infinity t to the power n is absolutely convergent. Okay, this implies that t to the power n tends to 0 as n tending to infinity. Okay, now we're also going to this here I difference t multiplied by I plus t square plus t cube dot t to the power n equal to I difference t to the power n plus 1. So here we write this one tends to I as n tending to infinity. Why? Because norm t less than 1 and t to the power n tends to 0 as n tending to infinity. So we erase our portion and going to prove of that. Now here I difference t I plus t square plus t cube plus dot plus t to the power n equal to I. This implies R difference t be invertible with I difference t whole inverse equal to I plus t square plus t cube plus dot plus t to the power n. Okay, and obviously this one is because we know about that as n tending to infinity means this one is extant. Okay, so we write here this one equal to n equal to 0 to infinity t to the power n. So what we write here, I difference t whole inverse equal to n equal to 0 to infinity t to the power n. Okay, then we also discuss something. We'll erase that portion and going to further discussion of another important topics. We write this one is important for implicit function theorem. Okay, we just write now x equal to x1 x2 dot xn belongs to Rn and y equal to y1 y2 dot ym belongs to Rn. Then xy equal to x1 x2 dot xn y1 y2 dot yn belongs to Rn plus n. Okay, now we write here let a belongs to L of Rn plus m Rn. That means this operator from Rn plus m to Rn. Then we can write A of hk equal to axh plus ayk. this was belongs to Rn, this one obviously belongs to Rn. Okay, this one belongs to Rn and this one obviously belongs to Rn. Now A HK to this one, then we write in this way: AXH equal to A of H0 and AYK equal to A of 0K. Okay, then obviously this one written as in this way: A is defined as Rn to Rn and AY defined as Rm to Rn. Okay, now we're also going to be the implicit function theorem. Also write this statement first. Erase that portion and then we're going to prove. We write this statement here: let omega be an open set in R n m plus n and let if omega to Rn be a function such that first one f is continuously differentiable on omega. F is continuously differentiable on omega. Number 2, f dash ab equal to a. Then first one we write here: number a, there exists an open set U. There exists an open set U in omega with AB belongs to U and an open set omega and an open set W in Rm with B belongs to this W such that for each y belongs to W, there exists unique x belongs to Rn with xy belongs to U satisfies f of xy equal to 0. Okay, and then here we write for B, then obviously for B we write here f of AB equal to 0. Okay, and for C this one AX be invertible and AX inverse AY. Here AX inverse AY equal to minus C dash B. Okay, where G is a L1 mapping where G be a L1 mapping of W onto Rn and Gb equal to A and f of Gyy equal to 0. Okay, for y belongs to W. So this one is a statement near approximately one statement. Okay, we now prove this theorem. Okay, what we have to do, this one be an set, this one be an open set. Sorry, here we write be an open set in Rn plus m, and then f omega to Rn be a function such that f is continuously differentiable on omega and f dash a be equal to a. Then there exists an open set U in this omega with AB belongs to this U and an open set W in Rm with B belongs to W such that for each Y belongs to W there exists unique X belongs to Rn with XY belongs to U satisfies if XY equal to 0. And number 2, f of AB equal to 0. Okay, if xy equal to 0, then also shows that, sorry, f dash AB equal to 0. Okay, f dash AB equal to 0, and then we also show that g dash b equal to ax whole inverse ay minus g dash b equal to. Okay, so we step by step discuss this one. We now erase that portion. Now we also proof in next class. We just statement here and proof in next class I do it. So today we stop here.